Before looking at non-uniform circular motion, let's review some core ideas of uniform circular motion. For one thing, be aware that a problem must tell you that the speed is constant or that it moves with uniform motion. These sorts of key phrases have to be included, otherwise we really can't make that assumption. A good example of an object that does move with a truly uniform motion would be something like a Ferris wheel, where we can watch it move around. We can, recognize that there is a distinct connection between something called the period, which we wouldn't be able to talk about with non-uniform motion, or at least it wouldn't really have a connection to other things. So you can talk about period and speed, linear speed or angular speed, in a number of different ways. All of these different formulas that we've used in the past, these are all part of uniform circular motion. We also have the idea that there is a centripetal acceleration, because even though the speed is constant, the velocity is changing because there's direction that is changing. And so that is still going to be true. When something is moving in a circle but it's not a uniform motion, you're still going to have an inward acceleration. Something is changing the direction of the object. So although these are only for uniform circular motion, this is still going to be true. So we're still going to have that the radial or the centripetal acceleration is the linear speed over linear speed squared over r, or the angular speed times r, although we tend to use this version of it with more of these types of questions. And it's still going to be true that this will point inward, but it's not the only acceleration. There's going to be a tangential acceleration with non-uniform. So uniform acceleration, there is no tangential acceleration, no speeding up of the object. And so the net force points inward, the acceleration is only inward. Again, a simpler case that we started with. If we have non-uniform circular motion, how this differs from uniform, again, is that it's not going into constant speed, and so the velocity vector itself is changing in a lot of different ways. It may change speed, but it definitely it may change. I'm sorry, it does change speed, and it also changes direction, and so both the linear and the angular part of its motion are changing with time. So when we calculate that centripetal or that radial acceleration, we're still going to do it using the same formula. It's just that because the value of v is changing, then the value of the radial acceleration or the centripetal acceleration is also changing. We're also going to have a tangential acceleration, so that might be something we have to express like this, or it might come up differently. You'll kind of see this, but there is a net acceleration vector. These two things are going to be changing, and so they are perpendicular to each other. You can find like the magnitude of the acceleration by using the Pythagorean theorem, something like that. But let's take a closer look at what this might look like. Consider an object being spun on the end of a rope in a vertical circle. Okay, so you're spinning it so that it's only traveling vertically. I don't say only vertically, but the plane of the circle is vertical. Kind of like when someone does the bucket trick with water and they spin it around like that. So sometimes the bucket is at the top, and sometimes it's at the bottom, and sometimes it's at the middle. So we're looking at it from not downwards, but just from the side, and it's going in a circle like this. So the thing to notice here is that along that circular path, the motion is changing in a different way. It's going to be traveling faster at the bottom than it is at the top. And so there is going to be a greater inward acceleration down here, R, than there is up here. Okay, so how do we know that there's going to be a faster speed at the bottom? How do we know that this is true, that the velocity at the bottom is greater than the velocity at the top? Well, here's where our energy ideas come in. We know that in both situations there's going to be kinetic energy because it's moving. But if there is no outside force, if this is all controlled by a consistent tension force, then the energy has to be equal. Sorry, that should be an equal. The energy has to be equal at the bottom and the top. But at the top, there's also potential energy. And so that lets you know that this amount down here has to be bigger than the amount at the top. This is typically what we will use to find the speed, the linear speed, comparing maybe two locations, and then we would use that V to maybe calculate that radial acceleration. In terms of the tangential acceleration, that's a completely different set of forces, really. So if I look kind of at a sideways point, which we normally don't, let me switch to a different color. So if this is our tension force pulling inward, the thing is that there's also gravity pulling downwards. And so there's going to be a radial acceleration due to the tension force and determined by the value of V, but then there's also going to be a tangential acceleration, a tangential angular acceleration, or an angular acceleration as well. That's produced because at any particular moment there's going to be gravitational force. But again, this is going to change as it goes. Like if I were to switch to the top, now those two forces point in the same direction, and so I won't have a tangential acceleration, I'll only have the radial acceleration. And the same thing is true at the bottom. They will point in opposite directions. And so I will have a smaller net force and therefore a smaller radial acceleration, but there's nothing tangent to the circle, and so there would be no tangential acceleration. So again, in this challenge topic, try out a few of the questions, work through them. They're all a little bit different, so I'm not going to do an example, but think about both changes in speed and changes in direction. And so you have both radial acceleration and tangential acceleration.